Good afternoon, everyone. My name is Paul Steciuk with Northeast Power Systems. I'm happy to be doing this second presentation on harmonic filter design concepts. Just briefly, Northeast Power Systems is a manufacturer of metal enclosed harmonic filter banks and capacitor banks at the medium voltage level. That's our sole product offering. So we are quite involved with the design and construction of harmonic filter banks for both the utility and industrial marketplaces. So I'm going to bounce over to EasyPower just for a minute here. And I have a case up that I had up a couple weeks ago. And I just wanted to double click on the bus here and on the filter bank and show. So EasyPower has several different filter arrangements that are available to model in the system. In particular, the ones that are typically used in industrial plants and also at the utility level. The only ones I've seen in the last 20 years are the notch filter, which you see here, which is also shown in the diagram here. And a first order filter, I've never seen an application of a first order filter, so I wouldn't think that you'll get too involved with that type of filter. The second order filter, which is a high pass filter, is a very common filter. So between the filters that are available in EasyPower, the notch filter and the second order filter, or also the high pass filter, are the most common types of filters. So I'm going to just review quickly what those types of filters are all about, and then bounce back to EasyPower. So incidentally, this is a harmonic filter installed at a mine up in British Columbia. It's a 23 megabar, 5-stage harmonic filter system. And that's the type of equipment that Northeast Power Systems builds. So on the next slide is the one-line diagram of that harmonic filter system. And this filter system consisted of C high pass filter, which is here. So a C high pass filter is very similar to the high pass filter that's available in EasyPower to model. In fact, the performance of the high pass filter in EasyPower is equal to the C high pass filter that I've shown here. The primary difference is the capacitor that you see here, and actually I see an error in our mistake, an error here. So this is a C high pass filter. So we're going to go through the three types of filters. The most basic filter is the high pass notch filter that I've shown here. It has a very low impedance at its tuning frequency, and then it just shoots up linearly from there as it increases in harmonic number. This is by far the most common harmonic filter system used at the medium voltage level in industrial facilities. It offers a very low impedance at the tuning point, and therefore it's very effective at filtering harmonics. It's got low fundamental losses, but as you move away from the filtering point, its effectiveness at tuning drops off. The second type of filter that is available to model in EasyPower is called a high pass filter, and that's what I've shown here. And basically what we have is a resistor in parallel with an inductor, and based upon the ohms of this resistor, the characteristics of that filter change. And you can see here what I've done is I've plotted 5 different filters, 5 different values of resistance for the same size filter here. So I basically fixed the kVar of this capacitor, or X of C of that capacitor, and I've also fixed the inductance of this reactor, and I've varied R between, actually I'm just stating Q here, so I varied the resistance, and you can see that the characteristics of the blue curve, which is a Q of 10, okay, you have a minimal amount of losses in the resistor, and that's because that resistor value is a very high ohms. Okay, if you can think about a high pass filter, if you made it infinite, it would be a notch filter. In fact, the design of X of C and X of L, the choice of those values, is really dependent upon the tuning point, and then you vary R. So you can see that as we decrease the resistance, okay, or we change the Q factor of this filter, the amount of power consumed by the filter goes up. We start off at 1.6 kW per phase with a Q factor of 10 on this filter, and you can see that as we go down in Q factor from 10 down to 0.5, the kW losses inside this filter system significantly goes up. You can also see that as you drop the resistance, at the filtering at the fifth harmonic drops off. This red curve represents a Q factor of 1.0, and the most deepest curve here, the light blue curve, represents a Q factor of 10. You can see that the impedance at the fifth harmonic is much less. So by decreasing R, we change the characteristics of this filter, and you can see that our ability to filter at higher frequencies with lower values of R is improved. But that's not without consequences, because we have a lot more kW losses as we decrease R in this filter bank. So the last type of filter is a C high pass filter. And there is another EasyPower presentation that talks about C high pass filters. But a C high pass filter, in theory, it performs just like a high pass filter. In fact, when you model the high pass filter in EasyPower, you do get the same performance, although the filter parameters are slightly different, and the losses that EasyPower calculates are different, but the performance, in other words, the voltage distortion values that EasyPower calculates and the current distortion values that EasyPower calculates, they essentially are correct. The differences are the losses. And this filter, basically what goes on is we have a branch within the filter of the tuning reactor, X of L, and what we call the aux capacitors, X of C here, or X of C aux. These two values are tuned to the fundamental frequency. So as you apply fundamental frequency voltage on this reactor, the X of L and X of C are tuned to 60 Hertz, and therefore there is no impedance in this network, or is very low, and therefore there's no losses here. So a C high pass filter is very effective at reducing 60 Hertz losses, and by doing that, what we can do is we can decrease the value of R here, and in effect move towards one of these other curves where we have much more broader spectrum of filtering. Okay, so a C high pass filter is very, very typical of systems, especially that are tuned down in the second and third harmonic, that you would see in mine applications or in arc furnace applications, where you're trying to do low frequency tuning and there's a high fundamental loss. The other places you would see it is in wind farm applications, where you're trying to heavily damp the harmonic filter to get rid of a resonance, like cable resonance. Okay, so by putting a very low value of resistance into that filter, you get a lot more dampening and a lot more impact at higher frequencies, but you get a lot of losses. So one way to avoid those losses is to put a C high pass filter in. So just by way of example, on the left here I have a notch filter application where we just have 3 notch filters. On the right I have the same basic system, but I'm using high pass filters. If I were to look at the impedance scans looking into this bus, basically I'm doing an impedance scan by injecting 1 amp of current at this bus and plotting volts, or in this case, if it's 1 amp, it would be ohms on the other axis. You can see that for a notch filter, the blue curve here, you get very good and effective filtering at the 5th harmonic and the 7th harmonic and the 11th harmonic, but there are high peaks, these anti-resonant points that you get in a notch filter system. If I were to use the same filter system with a Q factor of 4, you can see that the resonant points are taken away. So in systems that have harmonics that exist between the 5th and the 7th inner harmonics, for instance, if you had like a 6th harmonic in this case, we would have a very high voltage distortion. We'd be trying to inject harmonic current into this high impedance and getting a very high voltage distortion. Typically, a high-pass filter or C-high-pass filter is used to avoid those types of situations. And finally, there's a other situation, and this would be more common for wind farm applications, where you install a notch filter and you have a system that has some kind of stray capacitance associated with it. When you have that, you will get a resonance at some higher frequency. A high-pass filter or a C-high-pass filter is able to avoid that resonance or dampen that resonance. So that's the application for these types of filters. So if I go back to EasyPower, so EasyPower has, if I look at the notch filter, there's only 4 parameters located for the filter for a notch harmonic filter bank. That's the megavar rating of the capacitor bank. So this system here is a 13.8 kV system. You can see that I've modeled 17.23 kV. And that's because filter bank capacitors need to have a higher voltage rating, because they will see a higher voltage duty when they are in application. Harmonic current flow through that capacitor in a harmonic filter system results in a voltage across the capacitor that the capacitor needs to be rated to withstand. In addition, this reactor that's typical in a notch filter or even a high-pass filter causes a fundamental voltage rise that's approximately equal to n squared over n squared minus 1 times the normal line to neutral voltage. So on a typical 5th harmonic filter, you might see about a 5% fundamental voltage rise. So for that reason, capacitor banks that are associated with harmonic filter banks typically have a higher voltage rating. Now, if we were to do the modeling at 13.8, we could certainly put 13.8 kV capacitors in this model, and the performance that you would achieve out of the filter would be correct, but the values or the specification of the filter would not be correct for an actual real-life situation. So it's kV line to line for that cap bank, and that's key. Some programs will use a line to neutral rating. EasyPower uses a line-to-line rating, and it's a 3-phase megavar rating for that cap bank. So basically, you're specifying this capacitor in a notch filter. The inductor you put in a value of ohms, which is the fundamental frequency ohms of that reactor. I'm going to get into how to calculate these values in a moment. And as a standard rule, I always use an X/R 100 for iron core reactors. Metal enclosed banks, the filter banks that NEPSI produces, are all iron core reactors typically, and they typically have an X/R on the order of about 100. So it makes it very easy in this case just to move the decimal point over 2 places. The other filter that's common is this is a high-pass filter. Really, the only difference here is you would model ohms for the resistor. So remember, there's a resistance in parallel with the reactor, and there is a value of R there. So you might ask, well, how do you pick R? How do you pick the resistance of the high-pass filter? And I'm going to show you that in a moment. But in general, it's safe to say that you don't want to decrease the resistance value of a medium voltage filter bank such that the kW losses in that resistor go, say, beyond 30 kW per phase. That's a typical range that I will stop at. So as you're designing your filter and you're looking for improved performance at higher frequencies, typically you start off with a high value resistance to have a very low level of losses, and you find that the system isn't performing quite well enough, your voltage distortion is too high or your current distortion is too high. You continue to decrease the value of ohms until you get some sort of system that meets IEEE 519 or meets the performance objectives of your study. So my approach is typically to start off with a relatively high value resistance and continue to decrease it until I get the performance I'm looking at. If the kW losses associated with that resistor, say, exceed 30 kW, then I start to question the design. You can go above 30 kW, but that's a good point to maybe start reconsidering the design and going in another direction. And as I'm on the subject of high-pass filters here, EasyPower is going to give you the kW losses in the filter for that high-pass filter, but bear in mind that a C high-pass filter, a lot of those losses, especially as you decrease the value of resistance, will increase, and a way to avoid those losses is to model a C high-pass filter. And again, there's an EasyPower presentation about modeling C high-pass filters in EasyPower. It's a very good presentation, and I would suggest you check that out. So let's talk about what EasyPower provides in terms of output. So when you run a EasyPower case and you do a summation all, basically we're looking at the harmonic current flow throughout the system for all the current injections throughout the system, and we're looking at voltage distortion and so forth. So at minimum, to get the data you need, you should have these items checked off: current flow, the current flow report, summation detail report, summation spectra report, and then a filters report. So one thing I can say about EasyPower and about most programs is that what EasyPower is doing is just calculating the expected current flow into the filters. So if I were to click on this, we have we can see that there is some data provided for the filter bank. We have the capacitor voltage, 13.8 kV, and we get some distortion and the voltage distortion and current distortion inside the capacitor bank, and we also get the losses in kW losses and kVar losses within the filter parameters. What I can say is that that is not enough to specify or design a harmonic filter. Looking at the other reports, this is a harmonic spectra report, and what I use this for is I usually come down and I grab the harmonic currents that the harmonic filter is seeing. Like right here, there's a filter stage currents. I can actually get the value of amps that the harmonic filter is filtering. And the point that I want to make to this is that the value of current that you calculate here should not be the design rating of your filter bank. The reality of the situation is that in most cases when you do a harmonic analysis, the harmonic current that you calculate is going to be much lower than what you want it designed for, because you want to have a significant margin in your design. So in this particular case, you can see I had a 60 hertz current of 41 amps into this filter branch, and I got a fifth harmonic of 4.88 amps. You certainly would not want to specify a harmonic filter that had a fundamental rating of 42 amps and a fifth harmonic current rating of 5 amps. And being a manufacturer of this, we often see specifications like that, where somebody has taken the output of a harmonic analysis program and sent it to us and said, design us a filter for that. The reality of the situation is this filter should be designed such that it contains at least roughly 20% overcurrent factor in the fundamental. At Northeast Power Systems, we actually will design the fundamental reactor current rating at 1.5 its nominal current rating. And then at minimum, the tuned frequency harmonic current should typically be at least 50% of the fundamental current. Even if you were to calculate 5 amps, as in this case, we would still recommend that the fifth harmonic current be at least 50% of its fundamental rating. So something like this, we would probably with 40 amps of fundamental current, we would probably specify a reactor that was rated 60 amps, and a fifth harmonic filter rating, we would apply roughly 30, at least 30 amps. So there'll be a significant margin there. So what we do, and I think what most consulting firms would do, is they utilize spreadsheet tools to help design filters. So do you use EasyPower to come up with performance parameters, the expected voltage and current distortion that you're going to get with the application of a filter. But then you use another tool. As a consultant, we often see other people, other spreadsheet tools that are being used. We have a spreadsheet tool on our website that we allow people to download and take. I encourage you to check it out. It's located at nepsi.com. If you're going to come in at the home page, and if you go over to the resource page under spreadsheet tools, we have a spreadsheet design tool called Harmonic Filter Design. It's a spreadsheet which I'm going to review with you now. So this is the spreadsheet tool, and I'm going to walk you through how this is typically done. Again, I would say most consultants are using a similar type of document. These are all password protected spreadsheet tools. If for some reason somebody would want to unlock it, we can provide them a password to unlock the tool. But it's a good practice to lock your tools up such that they don't get changed without you without knowing it. So this spreadsheet tool we have on our website, it can design notch filters, high pass filters, C high pass filters, notch filters that are delta connected, C high pass filters that are internally fused. So there's quite a few different sheets on this page, on this Excel spreadsheet. So the yellow fields represent the basic parameters of the filter. So in this case, if I were to want to design a 13.8 kV filter, and let me zoom in here. If I were to want to design a 13.8 kV filter and have it be 5,000 kVar rated, that's the kVar output of the harmonic filter, and I want it to be tuned to the 4.7th harmonic in 60 Hertz. I just enter those parameters, and the spreadsheet tool is nice because all the formulas that are used to make these calculations are shown off to the right. This is the design tool that we typically provide to our customers, and it's a design output that we would typically provide with our harmonic filters. So the values in white here are all calculated values, and it calculates the frequency of the tuning point, which is just based off 4.7 harmonic, but it calculates the effective reactance of the filter, which is basically the combination of X of C and X of L at the tune frequency, which is a combination of X of C and X of L at the fundamental frequency, which dictates the amount of kVar that you're going to get out of the bank. If I were to go further down, the reactor value of 1.81 ohms is the required ohms to tune a 5,000 kVar 13.8 kV bank to come up with that 4.7th tuning. It would have a millihenries of 4.79 millihenries. Here's that typical X over R ratio for the reactor of 100. So once you input the kVar, it calculates X effective, and it will then further calculate X of L and X of C. X of C being the capacitive reactance of the filter. So if I scroll down here, we're just coming up with the values of X of L and X of C. So once X of C and X of L are picked, you still have to come up with a voltage rating on the capacitor. And like I said before, a 13.8 kV system, if the nominal voltage of that system is 13.8 kV, you still will need to pick a higher rated capacitor. So at 13.8, the line to ground voltage, and these are normally Y connected. Almost all medium voltage filter banks are Y connected and ungrounded. You would typically pick a capacitor voltage around 9.96 kV. You might sometimes see some people will push the voltage rating down to 9.54 kV. So in this spreadsheet tool, it's basically asking, well, what cap voltage do you want to pick? And in this case, we picked 9.96 kV as a starting point, and it wants to know how many capacitors per phase. So at the medium voltage level, for everything above 4.16 kV, typically you can buy capacitors that are 50 kVar rated on up to about 600 kVar rated, and some manufacturers will actually go to 700 kVar on the individual cans. So capacitors at the medium voltage level are typically single phase, and since it's an ungrounded bank, they would be 2 bushing capacitors. So in this case, by using 5 capacitors, you can see that there's 5 497 kVar cans per phase. That's what would be the specified value. You could then take these values here and go back to EasyPower and input the three-phase kVar and the XFL value for the reactor, and then model the system. And that's something that we would do. We would typically use this tool to come up with the three-phase kVar and also the ohms of the reactor, and input them into EasyPower to design our filters. So if I were to continue down through the spreadsheet here, if I scroll down a little bit further, you can see I have a specified spectrum of currents that I will put in. So as a starting point, you can put into this spreadsheet the harmonic currents that EasyPower calculates. You go to the output summation report and you use those values as input to the spreadsheet. In this case, I have a fundamental current rating of 209 amps on the reactor on the filter bank. Okay, it's a notch filter, and I've put 200 amps in for the FIP. And this would not be uncommon. The objective here is always to design harmonic filters that have a lot of margin, especially iron core filters, because you want to make sure that reactor has a lot of margin in it. If you have a reactor failure, it typically makes a pretty big mess. So it is best to design with a lot of margin. So what you're striving for is a highly reliable harmonic filter system. So by specifying the currents here, this spreadsheet tool will actually calculate the 4 key parameters that are required to properly design a filter bank and choose the right capacitors. In this case, the spreadsheet is putting out the percent of rated volts. Okay, it's an RMS voltage. So when you buy a capacitor, it's going to have a rating, and in this case, we picked 9.96. That 9.96 kV capacitor has actually standard values for overvoltage, crest voltage, as well as the fundamental amps and percent kVar. So the spreadsheet, what it does is it takes the harmonic current that I've put into the model, into the values down here, which are different than what EasyPower put out, and we're confirming that the voltage rating on the capacitors are adequate. If I were to come down, go up and use 9.54 kV capacitors instead of 9.96 kV capacitors, you can see that at a 10% overvoltage in the system, my percent crest voltage is at 114%. Okay, but that capacitor has a rating of 135%. And incidentally, all medium voltage capacitors are not the same. In fact, you can see here I have 3 different choices. You can use standard duty rated capacitors, or you can use heavy duty rated capacitors, or extreme duty rated capacitors. And these are Cooper terms, but whether you're buying from ABB or from GE, those capacitors will have different values for overvoltage capability and crest voltage capability. So it's important to understand the capacitor you're purchasing or specifying. It's not just a matter of specifying a 9.96 kV rated capacitor or a 9.54 rated capacitor. You also need to know, is it a heavy duty rated capacitor, or is it a standard duty per the standard capacitor? If I were to kick over to the presentation here. So this is a picture of the 2 bushing capacitors that you would typically see in a harmonic filter bank. In North America, basically you're typically buying from ABB, Cooper, or General Electric, although there are some other foreign manufacturers that are also selling into the United States. But the standard voltage rating for these capacitors is 2.4 kV to 24.9 kV. Some manufacturers will go to 150 kV BIL, but some only go to 125 kV BIL. So 1 bushing, 2 bushing designs are available, but as I said before, medium voltage filter banks and industrial plant applications typically without ungrounded banks, so 2 bushing capacitors are utilized. And also, capacitors can come in as standard duty, heavy duty, or extreme duty. All capacitors are not created equal. That's the key here. and it is important that if you're specifying a capacitor, that you understand the capacitor that you're going to get. Or if you're evaluating a specification of somebody who has quoted you a capacitor bank, it's important to understand the type of capacitor that you're getting. All capacitors have a 5-minute discharge resistor in there to discharge trap charge. That's an IEEE standard requirement. So the capacitor standards, the key capacitor standards in North America are standard 18 and C22 in Canada. And then the European standards are the IEC standards for capacitors. There are 2 application standards, IEEE 1036 and then C37.99 for the protection of shunt capacitors. So the values that the program, the Excel spreadsheet is calculating are these 4 values here. Basically, a standard IEEE rated capacitor has a 110% voltage, and basically that's the summation of all the harmonics square root. So it's an RMS value on the capacitor, including the fundamental. So an IEEE capacitor, the standard is 110% of its name. It also has a standard of 120% of its peak rating, the capacitor. Okay, which basically here what we're doing is you're calculating the voltage rise for each harmonic that flows into that filter bank across the capacitive reactance of the capacitor, and you're summing up those voltage peaks and you're comparing it to 120% of the nameplate rating. There's also a harmonic, a RMS current rating of 135%. That's also applied to standard IEEE capacitors. Okay, and again, it's a summation of all the individual harmonic current square root. And the same for capacitors. So the spreadsheet tool that we offer on our website does these calculations for you once you input the data. This is the typical standard duty, heavy duty, extreme duty ratings that you would see applied to one particular capacitor manufacturer's capacitors. Their continuous overvoltage for their standard duty. These all follow the IEEE standard for values, but they also offer heavy duty and extreme duty, and you can see that there's a bounce in the overvoltage capability of the capacitor. So the typical cost to go from a standard duty to heavy duty is not all that significant. So in general, we always recommend to go with heavy duty capacitors because there's not a significant cost associated with it, and you do get a pretty good design margin, additional design margin of 15% on the continuous RMS voltage, and also on the peak voltage. And incidentally, peak voltage tends to be where you run into the problems as a harmonic filter brings in more and more harmonic current. It's the peak voltage that's typically the stumbling block for picking the correct voltage on the capacitor. All right, so going back to the spreadsheet tool. So the other parameter that needs to be specified is the harmonic filter reactor. Okay, so this spreadsheet, we actually tally up the harmonic currents. We provide a design margin on the reactors. So typically we would provide a 50% design margin on the fundamental current rating of the filter bank of what that reactor is expected to see. And we would also put a design margin on top of the harmonic currents that we specify or that we expect to get. Do that is because iron core reactor design is somewhat of an art. So you want to put some margin in there from where you rate the harmonic filter to what you give the supplier of the iron core reactors. So it's an additional amount of margin. So just briefly on the iron core reactors, this what we show here is a picture of a typical medium voltage iron core reactor. Typically metal enclosed banks are always getting iron core reactors. It's very seldom that you'll see air core reactors associated with a metal enclosed bank because you have a lot of stray flux associated with air core reactors that cause heating in the enclosure walls, and therefore you typically see iron core reactors. Here you can see the reactors are put up on insulators. We do that because the typical voltage drop across a reactor is only on the order of 500 to 1,000 volts on like a 13.8 kV rated capacitor, on 13.8 kV rated harmonic filter, excuse me. So what that allows is for the insulation to not be stressed if we put the reactors up on insulators. So we basically tack the incoming winding, the incoming line to the core, which raises that reactor up in voltage, and therefore the normal voltage during operation across this insulation is on the order of 500 to 1,000 volts. So the reactor still gets designed for the full system voltage, because during inrush or energization you do get full voltage stress across the winding. So therefore it needs to have the full insulation, but during normal operation it sees almost no stress, so it makes for a very highly reliable design. Like I said, typically we are using iron core reactors. There's some advantages to use iron core reactors, and especially inside metal enclosed banks. There's no stray magnetic fields and it's easy to enclose. They shipped installed inside the filter bank. And they have much shorter lead times when compared to air core reactors. There are some disadvantages. One of those is they're susceptible to saturation. And that is one of the reasons why it's very important that the iron core reactors get properly specified. So just showing a couple of pictures. On the left here I have an air core reactor. These can be very large, sometimes on the order of 5 feet. And then they also need an additional 5 feet of space on each side. So you're talking about this for one single reactor area of about 15 foot in diameter. And they would typically stack 3 high. To the right here I show a single phase iron core reactor. So at the medium voltage level, it's very typical that the reactors are single phase, but there are occasions when the reactors will be 3-phase, especially the smaller filter banks that might be on the order of 1 or 2 megavars. So here I show a picture of a typical stacked reactor arrangement. This is an air core filter bank. What you see here is high pass resistors stacked up alongside a set of air core reactors and then an open rack capacitor bank. In some cases the reactors get so large that you need to put the reactors down at ground level. So you can see there's a lot of area associated with this application. So for iron core reactors, what's typically specified to a reactor manufacturer is, number one, is how many phases are the reactors. And like I was saying, there's a possibility that 3-phase reactors will be used on smaller banks that are on the order of 1 or 2 megavars, maybe even up to 3 or 4. But after that, typically at the medium voltage level, you're going to get into single-phase reactors. You're going to need to specify inductance and reactance values, and the reactance is normally specified at the 60 hertz value or at the 50 hertz value if you're in Europe. The manufacturer wants to know what the nominal system voltage is. That helps them determine the insulation class of the reactor. Okay, so if it's a 13.8 kV system, typically you're looking at a 95 kV BIL. And it also lets them know what the margins are, and that margin is the distance between the winding and the core, and that's a creepage distance that they need to determine based upon the voltage class. The reactor supplier will also want to know the RMS current, and this is from that same spreadsheet tool that we have. This is typically what we will paste in to our supplier to let them know what they should be quoting. So here you can see that we're calculating RMS current for them, and they need the RMS current so they can rate the winding ampacity. They need to pick the magnet wire that's going to be used for the iron core reactor, so the RMS current is something that they use for that, and also determines the cooling requirements for that winding. And as you can see, we also specify harmonic current on a harmonic basis. So in this case, we have the fundamental specified and the fit specified with the design margins of 1.5 based upon what was in the spreadsheet. So the harmonic spectrum, current spectrum, is also necessary because each harmonic current flowing into the reactor will produce flux that the core must be able to carry. Okay, so it's important that the supplier understand what the spectrum of harmonic currents are. So you have your program that puts out a harmonic current, but then you have the margin that you're going to add in any additional current. And that's what the reactor supplier wants to know, and that's what you should provide them, is something that has a lot of rating to it. So a harmonic current, higher frequencies cause more heating in the core, so therefore it's important that you specify those. And then finally there's taps. Iron core reactors often get taps. You tap the harmonic filter to allow for the movement of the tuning point within the filter bank. There's a lot of different things you can do with taps. I mean, the most basic thing you can do is you provide plus minus 5% taps or plus minus 10% taps. But there's also the ability to provide taps such that when you change from one tap to the next, you change the filter tuning point. For example, I might have a system that consists of 4.7 tuned filters. But there's an option where I can put a tap on the second stage reactors such that the 4.7 tuned filter can be tuned to, say, the 6.7 harmonic. And then the third stage, we could tap that one to be at the 10.7 harmonic. So what we essentially do is we can tap each of the stage reactors differently, such that if for some reason the performance that we were expecting to get or hoping to get from our fifth harmonic filter design is not adequate, we can tap the second, third, and in this case fourth stage reactors to allow for tuning at different frequencies or higher frequencies. You can also use taps to allow for expansion of the filter. That's another thing you can do. So an example of that is a customer might say, well, I want a 3 megavar harmonic filter bank, but I want to have the ability to expand it in the future. Okay, so what we would do is we would provide a 3 megavar filter reactor that tunes the bank to 3 megavars, but then we would also put a tap in there that would allow the customer to put in 3 additional megavars of capacitors, and we would then retap the reactor at the 6 megavar tap. So you can save in cost with a future expansion on the filter bank. And the last rating that's typical is to specify an ambient temperature rating. For iron core filter designs inside metal enclosed banks, we would recommend that you use a 60 C ambient because it can get hot inside the enclosure. So the reactor designer should know that he could expect 60 degrees C ambient for his design. So I'm going to go over the other spreadsheet real quick. Got a couple more items. So that was basically essentially what the spreadsheet, the notch filter design. What we're doing there is just coming up with all the parameters to specify the capacitor and reactor requirements, and also the fuse requirements for that filter bank. The spreadsheet also puts out an impedance scan, and you could get the same thing in EasyPower. So this is just another tool, and then we calculate some losses that we could expect out of the design. These are all estimates. So high pass filter, the spreadsheet is exactly the same. The only difference is that we can specify a damping factor, and the damping factor is equal to resistance divided by the tuning frequency times XL. So basically, it's the R over X value at the tuning frequency of the filter bank is what the damping factor is defined as. So in this case, we can change the Q factor up and down. You can see that as we decrease the damping factor, the kW per phase will go up quite a bit. So this is what we typically do here when we design our. I can show you what I would typically do is I would design such that my high pass filter has a shape like this at first. I could certainly change the Q so it's much steeper like this, which resembles a notch filter, And if you were to model this in EasyPower, you would not get much of an impact. So my approach is to come into this spreadsheet and scroll down the resistance value until I get something that looks somewhat like a high pass filter. And again, that's pretty much of a notch filter still. So you pull it down. Maybe something like this, 5. You can see that this is starting to look more like a high pass filter. At the tuning frequency, we're not down to near 0 ohms. And this might be something similar to a starting point that I would start at and then see what my performance is. So basically we discussed the reactor ratings and the capacitor ratings and how we come up with those. Also, you have, once you do come up with your resistor value in ohms, you would specify the ohm value to the resistor manufacturer, also the system voltage that you expect to apply the resistors at. And resistors are done just like the iron core reactors. They're put up on insulators, and the resistors are tied to the incoming winding. You would specify watts to the resistor manufacturer also. And it's important that at least you double what you calculate for the resistor. And again, it's very important that you have a lot of margin in the resistors also, because there are things that occur on the system that you may not account for. So it's typical that you at least double the rating from what the filter is designed for. And let me just show you real quickly. So this is a picture of the high pass resistors up on top. Typically high pass resistors are a stainless steel grid resistor, and they do not require cooling fans. They're usually in a very highly ventilated area, and it's a grid style resistor. And this shows one being dropped in place on top of an enclosure here. So once you have the R, L, and C figured out, there is still a lot to do with the specification of a harmonic filter. This is a one-line diagram of a harmonic filter, and you can see that there are still a lot of other things to specify. In this case, you still have to specify an incoming air disconnect switch, lightning arrestor ratings. There's going to be some kind of protection associated with this equipment. At least you need over voltage protection. You're going to need some kind of over voltage protection. You're going to need over load protection also. And then you also need to specify switching devices. What are you going to switch the branches with? What type of device? It could be a contactor, it could be a vacuum switch, it could be a vacuum breaker, it could be a lot of different things. So it's important to understand the ratings of those devices, how to apply those devices, and how they impact cost. Then of course you have the fusing on the capacitors. If they're externally fused capacitors, you need to size those fuses and specify the fuses. And finally, there's blown fuse detection, which can be done in several different ways. We could use neutral voltage sensing or neutral current sensing in a split Y cap bank. We can also use direct fuse sensing. So other than RL and C, there's still a lot to do with specifying a harmonic filter that you need to be concerned about. And finally, our web page does contain a lot of different specification values, a lot of different specifications. I can show you where they are. They are located under the resources, guide form specifications. And here you'll see that we have several different harmonic filter specifications, some for wind farms, some for chemical plants. So filter systems and capacitor banks, for that matter, typically have a certain configuration that's somewhat standard to the industry. Wind farms and solar plants are typically at 38 kV. They utilize certain types of switches. So we develop specifications by industry application, and they are available on our website under the resource menu. All right, well, thank you for attending the webinar.